All right, so I'm going to be talking about SIA, which is a secure intermittent architecture for off-the-shelf resource-constrained microcontrollers. It was presented at Host 2019, and it's by a group from Virginia Tech. So brief introduction to intermittent computing. It's mainly used in systems using harvested energy, where you don't have, your device is not constantly powered. So most programs will not complete during the short time that your device is actually powered. And so if you were to plot some measure of progress against time, you would get a graph like this, where when your device is on, you make some progress, but you lose, as soon as you lose power, you lose all of that progress and you have to start from scratch again when your device, the next time your device is powered, and that same cycle repeats, and you never really reach, your program never really completes. And so, what you need to do is actually keep saving your volatile state to non-volatile memory. And so, if you do that, then when your device loses power, the next time it comes back on, it can resume from the same place where it left off, and eventually your program can complete. So forward progress requires saving volatile state to non-volatile memory. Now, this transition between states needs to be protected along with the power off state. And unlike regular devices, these are highly resource constrained devices. They don't have memory management units or privilege levels. So that poses a challenge for securing them. So let's look at the main contributions of SIA, full form is Secure Intermittent Architecture. Um, Guarantees software module security in both the power on and power off states. Um, it additionally provides three security services, which is self-attestation, so that the module that's running can make sure that it hasn't been tampered with while maybe the device was powered off, or maybe even while it was powered on due to software bug like a buffer overflow. Remote attestation allows a software provider to make sure that the devices it has deployed in the field haven't been tampered with, in terms of both the code running or the data that's being saved on the device. So the software provider can make sure that an attacker hasn't compromised a remote system. And the third service it provides is secure communication between the software provider and these devices that they've deployed remotely. And their implementation uses off-the-shelf hardware, doesn't use a custom tool chain, and it can be deployed via software updates. So existing devices can, this can be deployed to existing solutions. All right, so since this is a security architecture, we need to know the attacker model. So in this case, the attacker can read and modify network traffic, so it has control over the communication channel. Can manipulate all the software modules on the system itself, but cannot physically access the hardware. That being said, any hardware protection mechanisms that the software provider wants to deploy, they can deploy, and they are obviously encouraged to deploy because they don't affect SIA itself. These two things are independent. So let's talk about the design. So let's start with software module protection. So the goal is to prevent, uh, if there are multiple modules running on the system, you want to prevent them from interacting with each other, reading uh, the other one's memory and such. So SIA achieves this simply by leveraging memory protection features that are already available in these low-end microcontrollers that are commonly used. And these in turn are based on some sort of program counter-based memory access control, right? And so any program that you compile, it'll have multiple sections. So there are three important protections that you want to protect in this case, and SIA calls them, it renames section to SIA text, SIA const, and SIA data, which, um, as you would expect, correspond to the text data of the actual code for your program, the constants that the program uses, and the data section. Um, Finally, you want to disable debug and test interfaces because that's an additional attack vector that you, you obviously don't want to be exposed. Um, so how does this apply to intermittent, the nuances of intermittent computing itself, right? So any snapshot that you create during the checkpointing process needs to be protected. So that checkpoint, that snapshot contains all of your registers, your volatile memory state, and all of that is stored into non-volatile memory. So if you do that, if you store these checkpoints within a protected memory region, as described in the previous slide, um, then you've essentially protected your snapshots as well. Um, in addition, the checkpoint routine that performs this checkpointing, you also want to store the code, constant, and data sections of that routine also in protected memory. Um, so regarding the three security services that are provided, we need to talk about the cryptographic primitives required. So attestation and secure communication require a key derivation function, message authentication code or MAC, and an encryption algorithm. Now, you can use individual algorithms and stitch them together for each of these three primitives. But there's a single primitive called authenticated encryption with associated data, or AEAD, which provides all three of them. And using an AEAD is more efficient than using the individual algorithms. Um, Naturally, because these are resource constrained devices that we're targeting, that efficiency matters a lot. And so let's talk about how we use AEADs. The first thing is, let's talk about key derivation, right? So the key in question will be used for both authentication and attestation and encryption. So you want the module key to be unique for each module, and you also want it to be unique across devices. So if the software provider is deploying a single program on multiple remote devices, you want each of them to have unique keys. And so the way this is achieved is you compute uh, you use as input the contents of the text and the contents of the text and constant sections of your deployed program, and compute a MAC over them, and that's essentially your module key. And to make sure that it's unique across devices, The software provider can embed a serial number. Obviously, the serial number needs to be itself needs to be unique for each device. So the serial number is embedded within the const section. So that ensures that the module key itself is unique for each module and for each device. And a remote software update can trigger a change in the module key. So if the software provider thinks that there might have been, something might have been compromised in the field, they can reset the module key via software update. So let's talk about attestation. So the message authentication code, or MAC, in this case, would compute a tag over some data that we need to authenticate with the module key. Now, the data can be a challenge that's sent by the software provider. So that would be that's what they call fast attestation. That's a relatively short process, or it can be the entirety of the module memory, which includes the text and constant sections, not the data section, because that's subject to change, of course. But the text and constant sections, and that is what they call slow attestation. So what they recommend is, you can run fast attestation maybe multiple times a day and slow attestation maybe once a week, right? And so the figure on the right represents the slow attestation process. So you have your constant, your text, your module key, and the challenge sent by the software provider. And you generate a tag, and that's used for um, authentication as well. Finally, self-attestation is the same thing. So the text and constant sections, but without the key and the challenge, right? So basically, what you're doing, it boils down to key generation, right? But the module will compare that to the module key that it already has stored, right? And so if it computes this and it's the same as the module key that it already has, it knows that the text and uh, constant sections have not been tampered with. Um, right. So once you have all of these cryptographic primitives in place, secure communication itself becomes relatively straightforward. Obviously, you have to encrypt all the messages, using the encryption algorithm of your AEAD. Include a nonce for freshness, so that you don't have repeated plain text attacks. And you use that authentication tag that I mentioned earlier for verifying integrity and authenticity. Let's move on to evaluation. So they implement this on an MSP 430 with FRAM as its non-volatile memory. They measure three metrics: binary size, which is quite important because even the non-volatile memory of these systems is quite limited. Execution time and energy consumption. And they do this for four AEAD algorithms that are listed here. One of which is based on AES, for which MSP 430 has an inbuilt hardware accelerator. And you'll see, as you would expect, that affects the results quite a bit. So, as you said, binary size, the overhead is quite minimal, right? As mentioned earlier, AES is uh, has the hardware acceleration, so there's minimum number of additional instructions to be added, which is the 0.22% overhead in the binary size. Um, and NORX has the highest overhead, but it's still 1.35%, so it's not much. Um, so this table shows both time and energy consumption for each of the three services provided by SIA. Now, slow attestation depends on binary size. And so you see that showing up in the numbers here. Whereas fast attestation is constant. Um, and yeah, for communication, the message size is once again variable. In this case, they've set it to be the same as the size of a single block in each of the in for each of the encryption algorithms used here. Um, NORX is the second best after AES. So presumably, if you're using a device that doesn't have hardware acceleration for AES, NORX would be uh, the AEAD algorithm of choice. Um, Next, they measure the time required to attest 40 kilobytes of data, and they plot this against different checkpointing intervals, where the checkpoint interval is it's not really a time interval. They've set the checkpoint interval based to be based on different amounts of data processed. And so you see here for um, time, right? The higher your checkpoint interval, um, the lower the overall time taken for attestation is. However, one thing to note is that if you set your checkpoint interval to be very high, when when you lose power and you start back up again, you're going to have to, you know, y- that computation interval is going to be much longer, which means each time your device restarts, it's going to have to do a lot more computation. Uh, so it's not always beneficial to use a longer checkpoint interval. You might want to stop maybe at this stage because it's going to have diminishing returns after that. Next, they measure energy. Uh, this doesn't show any sort of deterministic pattern when the checkpoint interval is varied. But once again, if you keep in mind that you're going to have to redo a higher amount of your computation when you increase the checkpoint interval, you probably want to stay on the lower side of the checkpoint interval in this case. Finally, they measure both time and energy to create a checkpoint for different stack sizes. So stack size basically uh, is a good proxy for your runtime memory usage. So it's a pretty linear graph. Uh, Obviously, it increases with your stack size. The important thing over here is that compared to the only other competitor that they mention in the paper for a stack size of 512 bytes, their energy and time is about 65 times less and 52 times less than the only other competitor that they have. So to conclude, SIA is a secure intermittent architecture that works on off-the-shelf microcontrollers and can be applied to already deployed applications, provides secure intermittent computing along with remote and self-attestation and secure communication. And the overhead in terms of both time and energy is negligible. So it's definitely something that's worth uh, deploying, and it's easy enough to deploy. So highly encouraged in this case. Right, thank you.